Um, right. So I'm not really solid on how least squares work. I know
Okay.
how to use the normal equation and stuff, but I just don't understand how or why it works.
Let me pull up the relevant section in the book. So I think the actual derivation of where the neural equation comes from is in lecture, and it's like a little bit involved, so I don't want to go like too in depth into it. But basically what you're trying to do is this equation is kind of like projecting all of your output space onto the images of your input space under A, right? So let's draw this out. Yeah. So if your image or column space is like this plane here, then what you're doing is you're taking some like other vector out here and trying to find the x that gives you this projection, right? So that's going to be like some x hat that we're taking the transformation of. And we can call this vector we're trying to find b. So the idea is because when we take projections, right, the subspace here has an orthogonal complement. So we're also trying to find this distance here. This is b minus this approximation. And because you can kind of decompose your output space b into this projection and this other vector, there's always some approximation you can do given by like some projection matrix, right?
Right.
So that's kind of like conceptually what's going on, and like the actual derivation of the equation is a little bit lengthy. I would rewatch the lecture where we did that to see that. But if you like know the conceptual part like this, and you have that, you're like comfortable actually solving this equation, at ax equals, whoops, that should just be a transpose b. If you can actually like solve this or know different cases, like when A is literally independent columns or not, you should be fine for the midterm.
Oh, okay, sounds good.
Yeah. And then if you wanted to go over like any like true or false with those, you could go over the ones in the book, or if there's questions from the practice midterm, we can also do that.
Okay.
I don't think this came up too much in the practice midterms.
Yeah, it didn't. Which is like, I didn't get a lot of practice, so I just didn't really get it, but it makes sense.
So the midterm goes up to cover 7.1 and or just up to chapter 6.
It's just up to 6.
Okay, cool. Yeah. Anything else you want to focus on specifically, or anyone that just popped in?
Nothing specific for me.
Okay, cool. Let's go through third practice exam then. Do you want to start with the true or false, or some of the more computational questions?
True and false sounds good.
Okay, cool. Let's do them in a couple of chunks. So, actually, do you have it pulled up?
Yeah.
Yeah, if you guys have it pulled up, let's go. Let's do A through E first.
Is this midterm 2 or 3?
3.
Okay.
So this one is going to start with, we have A and B are square matrices that blah, blah, blah.
Is this false?
The first one is going to be false, yeah. So anyone else want more time for the first few? Okay, so
No.
the first one, this is going to be false because when we expand this out, right, we have both this AB term and this BA term, and these two aren't necessarily going to be the same, so we can't write 2AB.
When will they be the same?
When is AB equal to BA? I mean, that's when that's when you take two matrices of like this form, which is it's like it kind of looks like similarity, but it's a bit stronger of a condition. Wait, this, yeah, there's like a specific characterization of them, but it's a bit involved to like actually classify all of these.
Okay.
Yeah. And the second one is if A has complex eigenvalues, or all complex eigenvalues, it's invertible.
I feel like it's true, but I don't know how to reason it.
Yeah. Oh, one more note on the last one. I'm not sure if this concept is covered in this book, but there's this concept of simultaneously diagonalizing matrices. And one of the ways you can have this is if you can diagonalize these two at the same time, which means there's some basis where these guys are both similar to a diagonal matrix with that basis, even if they may be different diagonal matrices. But it's like a bit technical and I'm probably outside the scope of this. So yeah, for this question, if we have complex eigenvalues in particular, what's not going to be an eigenvalue? Or let me rephrase that. So we have this condition for invertibility in terms of its eigenvalues, right? Does anyone remember what that is?
If there's n distinct eigenvalues.
That's going to be for diagonalizing the matrix.
Oh.
This is a little bit earlier from that chapter, where we were talking about the different like A minus lambda i's, right? So
Yeah.
if you have an eigen vector, that means it's in the null space of this, right? So what kind of eigenvalue gives us information about the original matrix? So what happens when I set lambda equal to 0?
Then your matrix equals 0.
Um,
Or,
I mean, this term lambda I is equal to 0, yeah. And then what does the eigenvector actually represent?
Just the original matrix.
Yeah, it's going to be the null space of the original matrix, right? If we have, some eigenspace where these vectors actually map to 0 times themselves, these vectors map to 0, and they're in the null space of A. So if our null space is not just the point 0, then it's going to be equal to the eigenspace of the eigenvalue equal to 0. So in contrast, if it is invertible, that means that 0 is not an eigenvector, right? Or sorry, an eigenvalue. Does that make sense?
yeah. I have a question about diagonalizability.
Yeah.
So does there have to be n distinct eigenvalues? There doesn't have to be n distinct
Oh, they don't have
eigenvalues.
to be distinct, right? So if you take like a matrix that's already diagonal, for example, like something that's like 2's along here,
Yeah.
then this characteristic polynomial, det A minus lambda I, it's going to be 2 minus lambda cubed. So what's happening here is that you have this eigenvalue that's multiplicity 3, but you only have one eigenvalue. What's going to happen with this is that the dimension of the eigenspace is going to be equal to this
Multiplicity.
yeah, algebraic multiplicity. So there are lots of matrices that are diagonalizable that don't have distinct eigenvalues, but their
Okay.
eigenspaces are high enough dimension. On
Yeah.
the flip side, if you have distinct eigenvalues, that means that it will be diagonalizable because your dimensions of your eigenspaces will always be 1 and at least 1, and then your algebraic multiplices are at most 1, so they'll be equal in that case as well. Right.
Okay.
So if this question, so if A only has complex eigenvalues, it doesn't have 0 as an eigenvalue, so it will be invertible, right?
Going back before to the algebraic multiplicities, could you possibly state the difference between algebraic and geometric multiplicity?
So when you have a characteristic polynomial, right, like something like lambda minus 2 squared, lambda minus 3, what's the algebraic? What we're calling the algebraic multiplicities are the how many times something is a root of this polynomial, right? So 2 is a double root because there's a squared power there. 2 has, or lambda equals 2 to be more precise, has algebraic multiplicity 2. But there's different polynomials that have this characteristic polynomial, and some of them have eigenspaces that are smaller and some have eigenspaces that are larger. When you actually do this computation, null A minus 2i, this null space could be one-dimensional or two-dimensional. here with this characteristic polynomial, you don't need like, I mean, you use all the information in the matrix to actually find this polynomial, but you don't actually use too much about the matrix in terms of like what's actually going to like actually computing the null space or column space or anything like that. And when you actually find the specific matrix A minus 2i, now there's a bit more computation we're doing actually finding some null space. And that null space itself could vary a lot more depending on which A we pick specifically. I think the example lecture was like the matrix I had above. This matrix has this one has three-dimensional eigenspace because it's going to be all of R3. And I think if you put a 2 here, that should make it two-dimensional now.
Okay.
Is that right? Does anyone?
Yes, I just watched this lecture earlier today.
Okay.
Yeah.
Yeah.
So that's what he did, where he had like E1 and E3.
Mm-hmm.
It's spanning those two.
Mm-hmm.
And then, so would that be a geometric multiplicity of 2 then?
Yeah. So now this dimension of the eigenspace is smaller, and that's what we call the geometric multiplicity.
Okay, that makes sense. Thank you very much.
Yeah. Cool. Any other questions about diagonalizability? Does anyone have an answer for C?
I'm guessing it's true, but I'm not sure.
Yeah. So an orthogonal matrix has n pivots in reduced row echelon form. So when does a matrix have n pivots when we look at its reduced row echelon form?
When all the columns are linearly independent.
Right. And what's that mean as far as like is like linear transformation?
1-to-1.
And also that's
Isomorphic.
although I mean those are all true, yeah. But the in particular, all of those are the same thing as being invertible, right?
Oh, right.
So if it has n pivots in reduced row echelon form, we know it's invertible. So the question is asking, is an orthogonal matrix going to be invertible?
Is that always true?
Yeah, and do you know why it's true?
No.
So what's the definition of orthogonal matrix? There's an equation that we were looking for.
Yeah, it's something about its dot product is 0.
That's for when matrices are orthogonal. So it's true that a matrix consisting of column vectors that are orthogonal is also, well, no, actually it's not. If the columns are orthonormal, then the matrix is orthogonal. But in particular, that's like kind of a roundabout way of defining it. I think in the chapter they first developed like, oh, what's the matrix with orthogonal columns look like? And then they say like another term is an orthogonal matrix is a matrix where A transpose is equal to the identity, right? And then they like prove somewhere that this is the same thing as having orthogonal columns. But this condition is the one we're looking for right now. And in particular, this tells us for these matrices are all going to be square, right? Orthogonal matrices are defined to be square. And in particular, this means that A inverse is actually its transpose.
Okay.
So if it has n pivots in reduced row echelon form, it's going to be invertible. And orthogonal matrices have inverses that are equal to their transpose. So this is going to be true. Right. Then D. A is similar to B. and B is orthogonal, then A is orthogonal. Any thoughts on this?
What does it mean again if A is similar to B?
So A is similar to B, means we have some matrix P that A is equal to PB, P inverse. And this is like the actual technical definition, but conceptually, I like to think of it as these two are the same layer transformation, just kind of represented with different bases, right?
Oh, makes sense. Yeah.
Yeah, and I think, and either in some notes or in the lectures, professor said this is kind of like you can think of these transformations as kind of being like isomorphic as transformations, just like how we have different spaces being isomorphic, which is like kind of a very vague, abstract way of putting it, but it's definitely like good intuition.
Mm-hmm. Then I think this is true.
Why you say that?
Oh wait, if A is similar to B, that it only goes in that order, right? It doesn't also mean that B is similar to A.
I mean, B is similar to A as well, because then you'll have P inverse, P inverse AP is equal to B. So you can just flip the P and P inverse in this kind of like form.
Yeah, I'm not sure.
Anyone else have thoughts on how we might go about showing this is true or false?
I have no clue.
Okay, yeah, this one is like pretty tricky. I think like if you try and like use your intuition, it kind of doesn't really help you one way or the other. So I think the probably the best way to do it is just like grind out the algebra, right? So it's going to be orthogonal if A transpose A is equal to the identity. And then we have, oh God, this is actually a mess. PBP inverse transpose times PBP, right?
Should that be P inverse?
Say again?
Should it towards
Yeah.
the right? Should be P
Oh,
B
yeah.
P inverse.
You're right, you're right. So then this is going to be P inverse transpose B transpose P transpose P B P inverse, right? And then when is this equal to the identity? So if we have, what we want is for this term to cancel and for these terms to cancel, right? And that's not always going to happen. Sure, the B transpose and B's will cancel because they're inverses, but we can't get this middle term to cancel unless P transpose P is equal to the identity, right? And that's going to happen when P is orthogonal. So for some matrices where we can write A is PBP for P and orthogonal matrix, it works, but not for any choice of P.
So does P transpose P equal to P inverse P?
P transpose P is equal to,
Like, can you Are those interchangeable?
Only when P is orthogonal, right?
Okay.
Because this is what it means to be an orthogonal matrix. That's like this equation, or equivalently saying that its transpose is its inverse. But like here, we're just, this is any invertible matrix P in the definition of similarity. So in general, P can be any matrix, right? It doesn't have to be orthogonal matrix.
So basically, this statement is only true if P is also orthogonal?
Yes. And see, what's a good example? So one of the ways you could think about this is like, if you write it with respect to some basis, right? Have some basis B. Just because A is a rotation, or sorry, just because B is like a rotation doesn't mean like with respect to some other basis, it's still a rotation, right? Like what you could be doing is having like really small vectors, right? Or yeah, like really small vectors and like really large vectors. And what's going to happen is with this basis, like rotating with this basis is going to actually like, you know, shrink and stretch vectors in our standard basis, right? Like intuitively, when we like shift something into this form, you're like going to have to like rotate and stretch at the same time rather than just have a rotation with the standard basis. Does that make sense?
Yeah.
Mostly, yeah.
Yeah, it's kind of a more like abstract geometric argument. Yeah, and then these questions make you find a counterexample if it's false. No need to provide an explanation, yeah. So like you can actually construct one, but there's like some algebra involved and I don't want to go too much into the computation of it. I think the conceptual answer is more than fine. So do you guys need a little bit of time to look at the next few, or you want to just keep going at them?
I'm fine with whatever.
Okay, so let's go on to E for every subspace H of subspace Rn. We have some A where the null space of A is equal to H. Is that true or false?
I don't get what the last part is saying.
So if H is some subspace, is there always a matrix that has a subspace as its null space?
So H is, so it's H in other matrix.
H is a subspace, right? So a subspace is some subset of Rn that's closed under addition, scale, multiplication. And they look like you know, lines, planes, hyperplanes. And that they have to go through the origin as well.
So if H was a subspace consisting of only zeros, then this would not be possible, right?
Wait, say again?
If, oh wait, actually, wait, never mind.
Yeah, so we have like this trivial subspace, which is just the zero vector. So I guess yeah, point as well, just the origin. But then any invertible matrix has null space equal to just zero.
Right.
So let me ask you a little bit of an easier question. If I say, here's R2, and I want you to find a matrix where the null space is the x-axis, could you do that?
Yes.
Yeah. Do you have like an example or?
Just something where only y is defined, so you can only move in the y direction.
Yeah, for example, you could take like xy maps to,
Like-
we want
It just can't touch that. Yeah.
x like 0, right? So
Yeah.
actually, no, I think I switched those, didn't I? Because the x-axis is where y is equal to 0. So we
Or
want
yeah, so it'd have to
0
be
y,
like,
rather. Oops.
yes.
So now everything on the x-axis maps to 0. Is there a reason that we couldn't do this for some other arbitrary line, like maybe this like line y equals x?
I think we'd be able to do that for any line then.
Yeah, and the same is also going to be true for planes in higher dimensions. For this question, your intuition about R2 will translate over pretty much perfectly. I won't like go through the actual process of constructing one of these matrices, but like, you know, if you can do it for this subspace, like basically just that same reasoning lets you do it for any other subspace. Questions about that one?
Okay, so the H subspace can't be all of R4 then, right?
You could
In
you could
order
take
to
it to
have
be
like
the whole
some kind of
space.
null.
Like
Or
you said
it-
R4, for example, like you could just take the matrix that's all zeros, right?
Mhm.
And then the null space of this guy is all of R4.
Okay, so okay.
Yeah. So yeah, I mean all of R4 is also like the hyperplane too.
Okay.
Yeah, you have basically like your smallest subspace is always going to be just the 0 vector, and any invariable matrix will have that as its null space. On the flip side,
Okay.
you could take, you know, all of Rn, and only a 0 matrix will have that as its subspace, or null space rather.
Okay, that
Yeah.
makes sense. Then all of them will have the 0 vector.
Yeah, so the 0 vector
Okay.
will be in the null space of every matrix, yeah.
Okay, right. Yes. Thank you.
And that's why I said like these subspaces go through the origin. That's kind of like the corresponding fact for these subspaces versus like the null space of a matrix.
Thank you.
Yeah.
That makes sense.
So if lambda is an eigenvalue of A, then lambda squared is an eigenvalue of A squared.
I think it's true.
Yeah, this to be true. And do you know why?
Well, if you just write ax equals lambda x and square both sides.
So yeah, pretty well. You can't square both sides because like this is going to be a vector, and then like when you square a vector, like there really isn't a good notion of like what means to square a vector. But what you can do instead is you can apply this transformation A to both sides, and that is going to do the same thing essentially. Right. So left-hand side, this is just a definition of A squared x. On the right-hand
Oh, yeah.
side, lambda x, lambda is a constant, so you can write this as ax times lambda, and then this is also lambda x.
Okay.
Let's go through. Do you guys want to try question 2 now?
Or
Sure.
Yeah, let's have a few more computational ones. So give an example or explain why none exists of 3 non-zero or orthogonal vectors in R2.
what's the question?
We're trying to either find an example or show why one can't exist.
Oh,
Yeah.
I'm not sure if this is right, but could you say the standard vectors, as in like the E vectors?
So in R2, we just have 2 of them, right?
Oh, right.
We have
Oh, that's what it
1, 0 and 0, 1.
Yeah.
But we do have that these 2 are orthogonal. Could we find a third vector that's orthogonal to these 2?
No.
Yeah, and
Mhm.
why is that?
that would be an R3.
Yeah.
Right. So essentially what's happening is that, first of all, these 2 already form an orthonormal basis.
Yeah.
So that's one way of seeing that if you take the standard basis, you can't find any other vectors and that are orthogonal to it. And another fact we have is that, this is basically saying the same thing, but without taking a specific basis, is that orthogonal vectors are linearly independent, right? And excluding a 0 vector, I guess, because 0 is orthogonal to everything, but linearly dependent with everything. So that's just an edge case we have. But if we have linearly independent vectors, in R2, there's at most, we can only find sets of 2
So
linearly
you'll
independent
probably be asleep by the
vectors.
time I get back?
Probably won't be, no.
Oh.
I'll be awake.
Then I will call you. Or I will text you and see if you're awake. And if you're awake, I'll call you.
Yes, I'm planning on finishing this lecture. Maybe this will be like
Oh my gosh, you're so gonna be awake.
Emily, is
Oh,
your mic
sorry.
on? It's okay.
So question 2, whoops. Real 3x3 matrix of rank 2 with 1 distinct eigenvalue. Let me extract eigenvalue. So any thoughts on how we might approach this? Oops.
So my first thought is that if it has 1 distinct eigenvalue, then that eigenvalue would have multiplicity 3.
Yep. So
And I don't quite remember. So like the whole rank nullity thing is that would add up to 3 then, right? So if the rank is 2, the nullity would be 1, according to that, like the rank nullity theorem.
that's true. It doesn't help us too much, but I mean,
Okay.
what'd you conclude from that?
I was thinking, I'm not positive, I don't think this would be the case. I guess I'm not positive, but I think it might be possible if you did what you did above with the two, like the diagonals that were
Oh yeah,
twos that had the numbers
like that.
exactly, yes.
Okay, yeah.
Like that,
So
but then yeah.
we do want something like this. Yeah, that's a very good start. I like that. This guy is, what's the rank of this one again? This one, uh,
It would either be 1 or 2, but I forget.
rank is the dimension of the column space. So
Oh,
actually, shouldn't this be rank 3?
yes, never mind. Yes.
Yeah. But
So
yeah, that's on the right track. We want something that looks sort of like this, but there's a few other pieces of information we also need.
So my understanding of this is that for there to be one eigenvalue, there has to be only one value on all parts of the diagonal, but that means that we would have
Yeah.
3 pivots, meaning the rank would be 3. So I'm not sure how to do this.
So close. You're almost there. So we do want same entries on the diagonal. That's part of why like this matrix is a good start.
Could you do zeros all along the diagonal
Yeah,
and then
that's what we
have
want.
non-zeros in 2 other spots? Okay.
Right. So we could take something like this.
Yeah. Okay.
Right. So now these column vectors are going to be literally independent. There's 2 of them, but this one is literally dependent. So the rank is 2. And the only eigen value is going to be 0. Does that make sense?
Yeah.
Cool. And I think one of the key insights is like, so if a 3x3 matrix is rank 2, what does that tell us as far as like invertibility goes?
It's not invertible.
Yeah. So rank 2 tells us that the null space is dimension 1, which tells us it's non-invertible, which then tells us that this eigenvalue that we're looking at has to be, this one distinct eigenvalue has to be just 0. Cool. What's the next one we're looking for? Real 3x3 matrix with an isomorphism from col A to null A. So what do you guys think? What do these column space and null spaces kind of like look like in R3?
If it's isomorphic, then the column space should be it should have 3 independent vectors, right?
Say that again.
If it's isomorphic, that means it should have 3 independent vectors.
So if something is isomorphic to R3, that means we have a basis with 3 linearly independent vectors. But
Right.
these are both subspaces of R3. So we need to find, well, if you have 2 vector spaces or subspaces of the same dimension, they have to be isomorphic, right? Because given the basis, like B1, B2, you know, in 2-dimensional case, D1, D2, you can say this linear transformation where B1 goes to D1 and B2 goes to D2 is an isomorphism. So then the question is, can we find bases of the same size for the column space and null space? It might help to like recall that in R3, our subspaces look like a point, a line, a plane, or all of R3. Any thoughts on an approach we might try? Some theorem that could be useful? So let's go back to what we used earlier somewhere. Or yeah, what are we using here to relate the rank and null space?
Rank nullity theorem?
Yeah, so in this situation, does that help us? So the rank is defined as the dimension of the column space of A,
Plus
and
the
the nullity
dimension of the
is dimension of null space of A.
Yeah.
So what does rank nullity tell us?
Those would have to add up to, I guess in this case, 3 then?
Yeah, so we have, this is equal to 3. And if we're using this equation, is this ever going to be an isomorphism between col A and null A?
No,
Right, and why is that?
because they can't equal each other.
Yeah, so you only have 0 plus 3, 1 plus 2, 2 plus 1, and 3 plus 0, and none of those are equal to n. So they cannot be isomorphic.
Makes sense.
Yeah. So yeah, I think the key things to like note is that in a lot of these problems, we used a lot of like the smaller steps of the verbal matrix theorem kind of like implicitly. The more you like kind of like remember each little detail of this, the more it's like helpful to like reason about other things just because invariability like is related to so much. And then of course rank nullity is very helpful in actually constructing matrices or thinking about null spaces of certain matrices, especially are you talking about like null spaces of certain like we're looking at like diagonalizations or eigenvalues, eigenvectors, stuff like that. It's always helpful to have.
Mm-hmm.
Any other questions before the midterm?
Are there any tips you'd give us?
No.
Besides like make sure you know like the big theorems like these two, and definitely like don't forget definitions, which is not a huge deal because this test open book now.
Yeah.
Yeah, so if you do forget them, you can look them up. But like knowing the different definitions kind of like different equivalent formulations of the same thing. Like I said, how with orthogonal matrices, they have orthonormal columns, but they also satisfy that property, A transpose equal to the identity. Like the book may say like one definition is like the definition and then prove this other like equivalent formula or characterization. And it turns out like one of those can be much more useful in some situations than the other.
Okay.
Yeah. And also like just general advice, not specifically for linear algebra, definitely like sleep a lot, eat well before the midterm.
Yeah.
It's hard to do math when you're hungry or tired.
All right. Thank you so much.
Yeah, of course.
Yeah.
Good luck tomorrow.
Thank you.
Bye.
Out of curiosity, do you think this midterm will be much harder than the last one, considering the fact that it's open book and open note? Or
I don't think the fact that it's open book or open note will make it much harder.
Okay.
Yeah, I think like the goal is to like not stress everyone out too much with this whole situation. So making it unnecessarily hard would just kind of like not do that.
Yeah, because I'd heard horror stories of like in the past people having midterms like this that took 20 hours or something.
Yeah,
to do.
I think if you're expecting an open book take-home midterm, like if that's like what's outlined in syllabus, you can bet it's going to generally be fairly hard. But because this is kind of just like a last-minute fix for the online learning situation, it's not going to be like designed to be incredibly hard or anything. It'll be fairly standard.
Yay! Thank you. Okay.
Yeah, totally.
Have a great day.
Thanks, you too.
Bye.
See ya.
Thanks.